Okay, so yeah, so let's recap the block sphere, and while we do that, I will also again talk about the overall phase business. So we said that a qubit state is represented uh, in terms of two complex quantities, right? But then we said there's a normalization constraint, and then we said there is also the freedom of choosing an overall phase, right? Or in the sense, there's a freedom of um, there's an overall phase freedom. So you can only determine states up to an overall phase, right? So let me just mention this again. So if I have a quantum state psi and I have another quantum state lambda psi, okay, where lambda is some complex number. I'm not even saying that it's a phase, okay? It could even be something with magnitude. I'm just saying it's any complex number, right? Now, these two states are not distinguishable. Another way of saying it is there is no quantum measurement that you can devise which is going to tell you whether the state you have is psi or lambda psi. Okay, so furthermore, because of probability considerations, we say that states must be normalized, right? So I'll come to this probability part when we discuss measurement again. But since, states are normalized, instead of stating it like this, I might as well say that lambda is of the form simply some e to the I, I don't know what to call it. Let me say gamma, okay? And gamma is just some angle now, right? So when lambda is a pure phase, this is what we call an overall phase, right? And once again, it's the same idea that two states psi and e to the I gamma psi cannot be distinguished. So quantum states are only determined up to this overall factor. Whether you want to think of it as a complex number with some amplitude or whether you want to think of it as pure phase, they're only determined up to this overall scalar, right? So you can use this fact firstly to normalize the state, right? That's what we said. You can always divide psi by the square root of the inner product of psi with itself, and that's how you normalize the state. And also what this means is when you describe the state, that is one less real parameter to actually specify, because this is a degree of freedom which is not physically accessible, right? So Jyoti Raditya, I think, had this question. Does that clarify this for you?
Yes, ma'am. Thank you.
Okay, sure. Okay, so this is where we were yesterday, right? This is where we left off. We said that, so you essentially need only two real parameters to describe the state. Theta is an angle that goes from 0 to pi. Pi is an angle that goes from 0 to 2 pi. And they're exactly the so-called polar and azimuthal angles of your spherical polar coordinates, right? So if I pick an arbitrary point on the surface of a unit sphere, I can map it back to a qubit state by taking this angle theta, right? And associating that with the amplitude with respect to ket 0, right? And sine theta by 2 is the amplitude with respect to ket 1. And the relative phase is given by the angle phi that the projection on the xy plane makes with the x-axis, right? Okay, so there is, so as I said, the reason we choose a half angle here is to make sure that this is a one-to-one mapping, right? So the half angle in theta ensures that this is a one-to-one mapping. And one of the things I often like to point out to people is this Bloch sphere picture of the qubit immediately conveys to you the kind of power that additional power that quantum computing provides you, in the following sense, that I have these 2 points, the one on the north pole and the one on the south pole of the sphere, and if I mark these as my ket0 and ket1, right, that's my reference, right? So I have written this with respect to ket0 and ket1, and when I write it, when I parameterize it like this, then automatically ket0 becomes the point where the sphere intersects the z-axis, positive z-axis. Ket1 becomes the point where the sphere intersects the negative z-axis, right? These 2 points, if you want to think of them as your classical 0 and classical 1, then what this says is, in this picture, your classical bit can take exactly 2 values, right? Can exactly either take this point here or this point here. Those are the only possible states that your classical bit can take. Whereas, of course, the quantum bit can now exist anywhere on the surface of this sphere, right? So it's a huge expansion of state space that has happened, and the quantum bit can explore all the states on the surface of the sphere, which is a continuum finally, right? So we also marked out some other states, right? We have already seen the plus state, and we realized that the plus state is nothing but the state where the sphere intersects the positive x-axis. The minus state is where it intersects the negative x-axis. And we also marked out 2 other states, plus and minus I. So let me just explain what that is, recall what that is, okay? So these are the plus minus I states, right? Okay. So yeah, so now suppose I want to transform the state of my qubit from ket0 to ket1. I can visualize it essentially as a rotation in the Bloch sphere, correct? So if I want to transform from ket0 to ket1, remember we already saw this kind of operation. We said it's a quantum NOT gate, right? But now what does it look like in the Bloch sphere? What kind of rotation is it? It's a rotation about what axis?
Pi about x-axis.
Indeed. So this is essentially a pi rotation about the x-axis. Okay. So this geometric picture also gives us a very physical meaning to these quantum gates, right? So it's indeed a pi rotation about the x-axis, right? Now, if I want to map ket0 to ket plus, that's a slightly more complex operation, right? But of course, any operation on the surface of the sphere can indeed be broken down in terms of some sequence of rotations, right? Certain operations you can immediately see are specific rotations. So for example, once again, if you want to talk about the plus state going to the minus state, let's say, right? What is this?
Ma'am, how is it about the x-axis?
Because you're going from here to here, right? So let me draw this again. I don't want to spoil that picture. So this is my Bloch sphere. I'm here and I need to get to here. Oops, sorry, let's get one. Right? So this is the x-axis, right? So if this point has to come here, then it's a rotation about the x-axis. Right? So we can formalize this more. So if you want to see it as a rotation matrix, we will indeed see it as a rotation matrix subsequently when we discuss quantum gates. But I just wanted to already, yeah.
But ma'am, in this case, I mean the rotation from 0 to 1, this can be as a rotation.
Sorry, I didn't understand. Can you What was the question? You're breaking off.
If we make rotation about any axis or any line on the xy, also we get from
No, any line on the x-axis will not work. You will get to slightly different states, right? If you, for example, rotate about the y-axis, is that true? So can you rotate?
Yes, ma'am, it will still go to 1. Means it's
Yeah, there will
these
be an
differences.
overall phase, that's all. Yeah. Indeed, you can think of it as a rotation about any line on the xy plane. That is true. Yeah. Was that your question, Pratik?
yes, ma'am. Ma'am, then what's the difference between the specific x? I mean, the x gate or any other gate on the xy plane.
Yeah, because we will define rotation matrices, like I said, in terms of the x, y, and z gates. So I already introduced the x gate. So this I already said can be realized by what is called the x gate, right? That's what realizes this specific operation, right? See, the difference will happen when you start making superposition states. Okay, so when I have an alpha 0 plus beta 1, okay, now under the action of the x gate, this is exactly going to go to alpha 1 plus beta 0. But instead, if I were to rotate it about some other line on the xy plane, then there will be additional phases that come in, right? So it will not be this operation anymore. Okay, so the difference will come in, when I start making superposition states. But if you simply want to look at it
So
as 0
it is
going
like
to 1,
it's not a pure rotation. I mean, other than the x-axis, the other rotations are not pure rotations.
no, they are, well, why do you say other axes are not pure rotations? If you see, you have to
I
pick
mean, ma'am,
3
they introduces
orthogonal.
an extra phase to the rotated side vector, right?
See, I can define any 3 fundamental axes and I can make rotation matrices about those axes, right? So there's nothing that prevents me from drawing a 45-degree line here and defining a rotation matrix about that axis. I simply have to write down the corresponding state correctly and define the rotation operator correctly for that. That's all. That's always possible, right? It's just that we would like to break down, obviously, since we have drawn these x, y, z axis, I would like to visualize all my rotations in terms of rotations about x, y, and z. So in that sense, about an arbitrary axis will have to be broken down into a sequence of rotations about x, y, and z. Okay?
Okay, ma'am.
Yeah. All right. So let us move on. I had not intended to get into rotation matrices in detail now, but just wanted to point out that the block sphere gives you a geometric handle on things. You can visualize specific transformations like this immediately as rotations. Like I said, we'll eventually get to a stage where we will say that any qubit gate can actually be realized as a sequence of rotations on the block sphere, right? Okay. So I wanted to complete this by saying that +2 minus would be a rotation about so the way I would like to think about it as a rotation about the z-axis. Okay. Yeah, and so on and so forth. I made a point about the inner product yesterday, right, where I said that these sets of orthogonal states actually reside at opposite diameters on the block sphere, right, at the opposite ends of a diameter, right? So, yeah. So yeah, this is what. So I had 0 and 1, and they're both residing at 2 points, which are the ends of one diameter. Plus and minus reside like that, minus I plus I. So you can actually work this out, right? So if I have an arbitrary state psi like this, what would be a state that is perpendicular to psi, or what would be a state that would be mutually orthogonal to psi? Okay, so I will leave you to think about that a little bit. So this was one point, the transformations are rotations was another point. The third point is orthogonal states reside at the ends of a diameter. Okay, and so if I have psi as cos theta by 2, 0 plus to the I phi sine theta by 2, 1, what would be psi perpendicular? So this is an orthogonal state to psi. So it will have to be something ket 0 plus something ket 1. What are these coefficients or these amplitudes that are sitting here? Any guesses? Okay, so let me leave this as an exercise for you to work out. Of course, you have to tell me there's a phase factor also sitting here, right? So obviously these amplitudes have to be related to theta somehow, and this phase has to be related to phi in some way. So maybe I'll just leave this as a homework for you to figure out what would be a state that is orthogonal to psi in terms of theta and phi. Okay. All right. So this completes what I wanted to say about the Bloch sphere for now. Okay. Yeah. One final point, which is that this kind of a nice geometric equivalence, unfortunately, does not exist for higher dimensional quantum systems. Okay. So this is just a two-dimensional quantum system, right? And we were able to get a very nice geometric picture of this C2, right? But such a neat correspondence does not exist. So I just want to point out that such a correspondence does not exist in higher dimensions. That is, for a D level system, you cannot do this. So for example, if I go from, so just as C2 refers to a qubit, I can think of C3, which is the space of three-dimensional, which is a three-dimensional complex linear vector space, which I can represent in terms of a column vector with three complex entries, right? So this is often called a Q-trit, right? So for a Q-trit space, I do not have this nice equivalence that every state resides on the surface of a sphere and things like that. Okay. So this is one thing to note. The other thing to note is I have really not said anything about the interior of the sphere, right? I have not even said anything about what the origin represents. Does it represent something? Do points in the interior represent anything? Or is it just that we stop with this identification with the surface? Well, it turns out that points in the interior are very important and they do represent something. But what that something is, we will see after we discuss the idea of measurement a little bit. Okay. So just to mention the word here, in case some of you are familiar with this, points in the interior represent what are called mixed states. Okay. They are mixtures of states that live on the surface. Okay. Of course, this is some very abstract statement now, but we'll make this more concrete, right? So you can see that, right? So if I have to take a point here and ask what does this point represent? Geometrically, you will tell me that this is some combination of this point and this point, right? It's a convex combination of the North Pole coordinate and the South Pole coordinate, right? So we can exactly write down a quantum state like that, which is a mixture of the state here and the state here, not a superposition, because all the superpositions reside on the surface, right? Any superposition of ket 0 and ket 1 resides on the surface. So what's inside is a slightly more complicated beast, which we will study hopefully next week, okay? So maybe I should just mention the terminology here. So these are also called density operators. Okay. All right. So all of this was a discussion that's, yeah.
Ma'am, you said that, all the superposition of 0 and 1 lies on the surface. I mean, that is the case because we usually have this requirement that our state should be normalized, right? That is the requirement that is leading to us working right now only on the surface and not on the interior.
No, points in the interior will not satisfy this constraint at all. If you're talking about unnormalized states,
Yes,
they will just be spheres of larger radius, not smaller, right? You answer what I'm saying. They will not be in the interior. If I want to talk about something like lambda psi, which is unnormalized, right, then that will represent for me the r coordinate, right, and that will only be outside the unit sphere. The normalization brings everything that is outside in some sense to the surface of the sphere. It doesn't tell me anything about the interior. See, what I have written down here are all what are called pure states, right? And pure states are mapped to the surface of the sphere in this way. What lives on the inside is not even a pure state anymore. Once I have drawn a certain sphere of a certain radius and identified states on the surface, what lives inside is no longer a pure state of this form at all. It's a completely different kind of object, right? We'll come to that. It has nothing to do with normalization, okay?
So,
Yeah.
so ma'am, that the definition which we had earlier defined, like the quantum states are represented by unit vectors in Hilbert space. So that essentially
Yeah.
applies to only the pure states, right?
Indeed, indeed. That is a restricted definition of the state, as we will see. Yeah, yeah,
Okay.
yeah.
Ma'am, another question.
That's a good starting point, right? But then it doesn't take into account, like I said, the interior of the Bloch sphere, right? So, yeah. Yeah. Question?
Ma'am, you used a word convex combination. What is that? Convex combination. I'm sorry, I don't know.
We'll come to that. We'll come to that. Yeah. I will explain. Yes. Okay. So to understand this convex combination, indeed, we should move on to the next kind of object. Actually, we should move on to subsequent postulates now. Let me say postulates 2 and 3, okay, which talk about observables or operators, okay, and time evolution. So we've seen what quantum states are, okay. Now the next question becomes, what are the physical quantities or observables on a system, right? Once again, classically, just as the state for me was a collection of position and momenta, right? So I can think of these as some position coordinates, and I can think of this p vector as some momenta, right? Observables are functions of position and momenta, right? So what do I mean by an observable? So for example, angular momentum is an observable, right? By observable, one means some physical quantities which are associated with the system, right? Of course, position, momentum are themselves observables, but you can construct other observables as functions of position and momentum, right? And since at every point in space and time, position and momenta are exactly described, these functions are also well defined, right? So you can think of angular momentum, you can think of energy, right? These are all functions of position and momenta, and these are all valid physical observables. But now states are vectors in a Hilbert space. Okay. So what are observables? Well, the second postulate tells us that observables are certain kinds of operators on a Hilbert space, and specifically observables are Hermitian operators on the system Hilbert space. So the first postulate identifies for you a certain Hilbert space which constitutes the state space of the system, right? And the second postulate says that the physical quantities that you can observe are associated with special operators on the system Hilbert space, namely the class of Hermitian operators. So what is a Hermitian operator? Once again, we will work with finite dimensions. So I will make this association of operators with matrices, right? Okay, so long as we are in finite dimensions, this is easy to make. This analogy holds even in infinite dimensions. It's just much harder. You have to think about this a bit carefully if you want to write down, for example, something like a position operator in matrix representation, right? But since we are in discrete finite dimensions, this association is much easy to make. In fact, in the early days of quantum mechanics, one of the terminologies used was matrix mechanics, right? So, that's sort of the underlying structure of physical quantities. Okay. So what are Hermitian operators? So let's define this formally. I know many of you know what these are, but there are some of you who do not know what these are. So let's define these formally. So these are also called self-adjoint matrices. Okay. So that word is already self-explanatory because the adjoint, remember, is this operation. So let me first say that this is what is called the adjoint. I don't know if I defined this in week 1. So adjoint is simply the complex conjugate transpose of a matrix. Right. So M star is basically taking the complex conjugate of all the entries of the matrix. Transpose, we all know what the transpose does. It flips around the rows and the columns of the matrix. And once you do this, you get what is called the adjoint of a matrix, right? And this is often denoted like this with this symbol, which is a dagger, right? So I will often say M dagger, okay? And this is what I mean. I mean the adjoint of the matrix, which is nothing but the complex conjugate transpose, right? And those matrices for which M is the same as its adjoint, right? M is the same as M dagger are called Hermitian. So M is Hermitian if and only if M is equal to M dagger, okay? So we have in fact already encountered some of these matrices. So let us look at some examples. So remember the X gate, right? The gate that was flipping you from 0 to 1 and 1 to 0, the quantum NOT gate. Okay. So what is its complex conjugate? I'm doing this only for those of you who do not know what Hermitian operators are. So please work this out with me, right? Yes, the complex conjugate is clearly itself because it's all real entries, right? And what is the transpose of this? Well, that's also the same, right? Because these rows and columns are exactly symmetric like this, right? It's a 2 by 2 off diagonal matrix. So this is also X itself, right? So you see that X dagger is X, and indeed this is a Hermitian matrix. Okay. So let's look at a few more examples. So let me write down a matrix that I call Y, okay? So this has entries like this, okay? Of course, all of you who have done physics courses know what matrix this is. So let me just mention here that this X matrix, which I will soon identify with a certain physical quantity, is often called sigma X, right, in the physics community. And this is one of the so-called Pauli matrices or the Pauli spin matrices, right? So it's one of a set of 3 Pauli matrices, right? And we said Hermitian matrices can be associated with physical observables. We will soon identify some observable with this, right? Okay, what matrix is this, physics people?
Pauli.
Okay, have I made a mistake with the minus sign, or is this correct?
Correct, ma'am.
Okay, just check and tell. Correct. Okay, good. Because I often put this minus sign in the wrong place. Okay, so now, yes, so people can check what is the complex conjugate of this. Well, the complex conjugate is no longer the same as Y, right? Because the complex conjugate becomes 0I minus I0. Similarly, if I only took the transpose, I will not get the same matrix. In fact, I'll get this matrix. But you see, if I now do complex conjugate and transpose, then I take the transpose of this matrix. So that then gives me 0I minus I0, which is simply Y itself, right? Okay, so I should mention that when I make this association with the so-called Pauli spin matrix, there has to be some dimensionality to this quantity, right? If I want to associate this matrix with a physical observable, I must provide it with some dimensions of the corresponding physical quantity, right? So in fact, the association is the following. It says that, yes, physics guys, what should I add to make this really a Pauli matrix?
H bar by 2.
Indeed, correct. So h bar by 2x is what I will call sigma x, right? So to be precise, sigma x would be the matrix h bar by 2, 0, 1, 1, 0. Okay. Now, I mentioned what h bar is when I spoke about spin half systems, I think earlier this week. So h is the Planck's constant. Okay. H bar is short for h over 2 pi. Okay. And this has the physical dimensions of angular momentum. Okay. All right, so I identified a second Hermitian matrix for you. And again, the association with the Pauli matrix happens via this constant number, which is h bar by 2. Okay. The third matrix, which I want to mention here, is the so-called Z. So you realize that when I write X, Y, Z, etc., they are the terminology that I will use for the quantum gate, right? So I will write this in a circuit as simply X to denote the quantum NOT operation. Okay? And the Y also can be written as a quantum gate like this, right? Again, maybe you guys can figure out what exactly the Y does. So what is Y acting on 0 give you? And what does Y acting on 1 give you? I'll give you a hint that we have already identified the states that you get by acting Y on ket 0 and acting Y on ket 1. We have identified these states on the Bloch sphere. Okay. So please tell me what you get by acting Y on 0 and Y on 1. Okay. Similarly, the Z matrix is this 2 by 2 matrix, 1, 0, 0, minus 1. Okay. This is what we will call a diagonal matrix, right? It's already in diagonal form with real entries on the diagonal, right? So this you can just look and say that this is Hermitian, right? So of course, Z dagger is the same as Z. This is very easy to see, right? And again, there is an association with the physical quantity, namely the spin, and this happens via the so-called Pauli Z matrix, right? This is another of the Pauli spin matrices. And of course, there is the quantum gate associated with it, right? And what does this do? So yeah, maybe I already discussed the action of this, but it doesn't hurt. So what does, okay, actually, let me look at this now. So let me look at what does Z do to 0 and 1, okay? Because I want to now make a point about eigenvalues and eigenvectors. Okay. So let's look at the Z matrix or the Z gate in some detail. So what is Z acting on ket 0?
0.
And what is Z acting on ket 1?
Minus ket 1.
Minus 1.
Minus 1. So what are these two equations? These are what we will call eigenvalue equations. Okay. If I want to make this more physical, I will say sigma Z, which is nothing but h bar by 2, 1, 0, 0, minus 1, right? So sigma Z acting on ket 0, which is the 1, 0 state. Remember, 0 is 1, 0, and 1 is 0, 1, right? Okay. Yes, what is sigma Z acting on ket 0? It is h bar by 2, ket 0. Sigma Z acting on ket 1 is minus h bar by 2, ket 1. So what I have actually identified by writing down these equations are the eigenvalues and the eigenvectors of the sigma Z matrix, right? So 0 and 1 are eigenvalues of sigma Z, okay? So I'm going to talk in terms of sigma Z rather than Z right now, because I want to make this point about the correspondence between the physical quantity and the operator or the matrix, right? And the corresponding eigenvalues are plus h bar by 2 and minus h bar by 2. So this then brings us to the reason why Hermitian matrices are the ones which are associated with physical observables. So the key property of Hermitian matrices is that Hermitian matrices have real eigenvalues. Okay. And because they have real eigenvalues, then the association is that the set of values that a physical quantity can take are the same as the eigenvalues of the corresponding Hermitian matrix. So this is how the association between physical quantities and operators works, that the set of values that a physical quantity can take are nothing but the eigenvalues of the associated Hermitian operator, right? So what is this sigma Z now? Sigma Z is what we will call the observable or the operator that's associated with the spin of a spin-half system, okay, or a spin-half particle. I should be specific here and say that the spin along a specific direction, namely the z direction, whatever we will physically call the z direction, right? That's why the subscript z, right? So the spin, suffice it to know for those of you who haven't done quantum mechanics courses and so on, we will just treat spin as an internal degree of freedom, which is manifest whenever there is an external magnetic field, right? And in this case, there is an external magnetic field along the z direction, right? Using that, you can probe the value of the spin along the z direction. And it turns out that the value of the spin can take exactly two values. So this is what spin quantization tells us, right? That the value of the spin can be either plus h bar by 2 or minus h bar by 2. So we'll see an interesting manifestation of this when we discuss measurement via the so-called Stern-Gerlach experiment. You guys can go and read up about it already. This was a pioneering experiment which actually showed evidence for the first time of spin quantization, that the value of the spin of a fundamental spin half particle can either be plus half or minus half in units of h bar, right? So this statement about the value of the spin observable being this or that can then be traced back to, oops, I said eigenvalues here. I'm sorry, I should have said eigenvectors or eigenstates. Is that what the question was about? Yeah, sorry. 0 and 1 are eigenvectors, also called eigenstates, okay, of sigma z. And the corresponding eigenvalues are plus and minus half h bar by 2. Yeah, was there a question?
Yes, ma'am.
Yeah.
So, ma'am, you are saying that the sigma z is giving us spin of a spin of particle, maybe plus half or minus half.
Yeah.
And physically, if we see, we are applying some kind of magnetic field, and corresponding to that magnetic field, either that spin half will be parallel or anti-parallel.
Correct. Yeah. Yeah.
So in that case, the sigma z operator is equivalent to some kind, say, I mean, applying sigma z operator over a quantum state is equivalent to applying that magnetic field over that quantum system.
No. So there are two different aspects to this, okay? When I say that there is an association between an observable and a physical quantity, the way I probe that physical quantity is by measurement, okay? So since you brought this up, let me quickly then get into this. The way the physical quantity is probed is via quantum measurement, right? And here's a cartoon picture of the quantum measurement for you of the sigma z observable. I have an input state, okay? And what the measurement, so this is my measurement apparatus, okay? I will make this a bit more concrete by talking in terms of Stern-Gerlach and so on when I actually discuss measurement, but since this question came up. So this is what I will call as an apparatus, okay? This is my measuring device, right? The state, so I'm drawing this again in a circuit kind of picture, right? Because at the back of my mind, I'm finally going to use this measurement in a quantum circuit, right? So this measurement, you realize, can have one of two possible outcomes. This is like applying the magnetic field. So this is like doing this. There is some inhomogeneous magnetic field that I apply. This is my fundamental particle, the electron, or beam of electrons coming in. So you know that now this spin is either going to align parallel or anti-parallel, and so this will deflect in one of two directions. This is the whole physical Stern-Gerlach setup, right? Anyway, details can wait, but the point is there are two possible outcomes, right? One corresponding to the plus half and the other corresponding to the minus half, or one corresponding to something that is parallel to the field and one corresponding to something that is anti-parallel to the field, right? Okay, so this is how you will probe the value, and each time you do the measurement, you can either get a plus half or a minus half, right? And that's why measuring this quantity is essentially like tossing a coin, and that's where the probabilities come in, right? But when I use this as a gate, right? When I use this as a gate in a circuit, that is very different. There, I put some arbitrary state in, I know exactly what state I'm going to get up. So if I put an alpha 0 plus a beta 1 here, I'm exactly going to get alpha 0 minus beta 1 here. This is a gate operation, okay? Mathematically, I'll come to what this is. This is not, now I'm not viewing this merely as a Hermitian operator. I'm making use of another property of this matrix, namely the fact that it is unitary, okay? That's a second class of matrices I wanted to come to, but maybe today we are already running out of time. But please note that there is a big difference here, okay? Here I'm probing the value of the physical quantity via a measurement. And here if I input alpha 0 plus beta 1, right, where 0 corresponds to the aligning and parallel to the field, and let's say 1 corresponds to aligning anti-parallel to the field, right? I don't know what outcome I'm going to get, right? I could get either this or this. So this is a measurement of the physical quantity, okay? Very different from applying a gate where this is deterministic. I know what the output is corresponding to this input. And it is the gate operation which is exactly like acting the matrix on the vector and doing this matrix multiplication. Measurement is not like that, right? Measurement is not simply sigma z acting on psi, because sigma z acting on psi, if psi is alpha 0 plus beta 1, will simply give me alpha 0 plus beta minus 1. I have not done a measurement here, I'm sorry. I have just transformed the state into something else, some other state, right? This is not a measurement. Okay, I can put a h bar by 2 outside if you want, because I put sigma. Okay. Is that clear, Nilesh?
Yes, ma'am.
Yeah, so this is a important confusion to resolve. Most people, I mean, it's a kind of tricky thing, and particularly with the Pauli matrices, because they are both Hermitian and unitary, this confusion often arises. But a measurement is something else. It is not this kind of a transformation at all. Okay, this is not measurement. This is the gate operation. Okay. All right. So we deviated slightly from where we wanted to be. Okay, so I was just giving the example of the spin half particle, the spin along the z, and I said the spin can be one of two values. This is the physical statement, that it can be either plus or minus h bar by 2. Mathematically, this translates to the eigenvalues of the corresponding Hermitian matrix being plus h bar by 2 or minus h bar by 2, and the corresponding eigenvectors are the spin eigenstates. Okay. Now, what does it mean to say spin eigenstate, right? So when I say that, so let me conclude with this today, and we'll discuss unitary operations on Monday, right? We'll discuss postulate 3 on Monday. So when I say 0 is an eigenstate of sigma z with eigenvalue plus h bar by 2, it means that if my system is in state ket 0, it has a definite value of the spin along the z direction. If my state is 1, it has a definite value, namely minus h bar by 2 of the spin along the z direction. If I were to draw this cartoon picture of measurement again, right, then what it means is if I have this measurement apparatus which measures sigma z, this is the apparatus, And instead of measuring an arbitrary state, if I were to measure the state ket 0, then what happens? Do I still get both possible outcomes?
You
No,
just
plus
get
h
ket
plus
0.
h by 2 only.
Yeah, so you only get the ket 0 outcome. The other outcome is not possible. Okay? That is what it means to say that a quantum state has a definite value of a particular observable, right? Similarly, if I were to input ket 1 to this sigma z measuring device, or if I were to measure sigma z on ket 1, I will only get this outcome. This is not possible. Okay? So this is why eigenstates are significant. It's important to identify eigenstates of physical observables because those are the states of definite value, right? States where the physical properties take definite value, right? Now let me leave you with this question. So you have to answer a few questions for me next time. One is, what is the state orthogonal to an arbitrary qubit state? That was the question I asked above. The other question that you'll have to answer for me is, yeah, what this Y matrix? Did you guys figure this out? The Y matrix? Y acting on 0, Y acting on 1, what does this do? Okay, so this also I will leave you to figure out. Yeah, tell me.
Y acting on 0 gives iota ket 1.
Is that right?
And another one minus iota ket 0.
Okay, good. So you see, this is a different kind of a NOT gate where you now have an overall phase coming into play. And this will become important when you do this in a superposition, obviously, right? Okay, good. So this is what the Y gate does. We already saw the contrast between the gate and the measurement, right? The final thing I want to point out is, suppose you have plus and minus states, right? So do these states take on definite values of spin? So the answer is no, they don't take on definite values of spin along the z direction, but they take on definite values of spin along a different direction, namely the x direction. Okay, so we'll start the next class with this. Okay, so the statement I'm making, and which you could check, is when I have the sigma x operator, then sigma x acting on ket plus will give me h bar by 2 plus, and sigma x acting on ket minus will give me minus h bar by 2 ket minus. Okay. All right. So let's stop here. Any questions?
Hello, ma'am.
Yeah.
Ma'am, I had a question about that when you said theta by 2 gives the one-to-one mapping. I didn't get that point, ma'am.
Yeah, so the point was this, that if I do not take a half angle, then I would say theta goes from 0 to 2 pi, right? If I let theta go from 0 to 2 pi, for the same theta, right? So let's say I have fixed this psi here, right? You realize that as I sweep through the phi, I access all the states on a kind of great circle here, right? But the same state here would be accessed by a different theta. right? So if I were to mark out a state here, there would be two values of theta that will map to this state. If I were to allow theta to go all the way to 2 pi. So I actually want to restrict my theta to go only from 0 to pi, right? And that is how I get a one-to-one mapping. It's a unique mapping, right? So you know your spherical polar coordinates, right? And you
Yes,
know
ma'am.
that you fix a range of these. Yeah.
No, ma'am, I was talking
Is that
about
clear?
the theta by 2 thing. Why did we take theta
Yes.
by 2 instead of theta?
Yeah, because I want to, okay, so if I were to allow theta itself, right, instead of theta by 2, then again, as I go from 0 to pi of my spherical coordinates, right, I will again be doing multiple mappings, right? So if I were to not have theta by 2, but just theta, right, then you will realize that theta 0 is sketch 0. What is theta pi? What is theta is
One,
equal to pi?
cat 1.
No, now it is 1. Now it is sketch 1 because of the half angle. But if I didn't
Yeah.
have the half angle and I had a full angle, if I had cos theta 0 plus e to the I phi sine theta 1, then
Yeah,
what
there'll
is
be
theta equal to pi?
It would have been 0.
It will be ket 0 itself with
Yes,
just a
ma'am.
minus sign.
Minus sign,
But
yeah.
those two quantum states are not distinguishable. So I'm kind of, I'll be mapping it back to this state itself. Do you understand?
Yes, ma'am.
So to keep this a one-to-one mapping and taking into account the overall phase degree of freedom, the correct parameterization is to use a half angle so that theta going from 0 to pi is your spherical coordinate thing. So yeah. So if you want to visualize this as a sphere with a one-to-one mapping of states, then the half angle is what you need to use. Okay.
Yes, ma'am. Thank
you. Right. Sure. Any other questions? Okay, so then I'll meet you all on Monday.